Thank you for coming to this one. There's some great talks on over there, and it's pretty sunny upstairs, so I really appreciate it. My talk's about real-time community detection in large social networks, and I do that on a single laptop. So first I'm going to explain exactly what that really terrible title means. And the data that we use is the full Twitter network. It's not trivial to get that, so I'll explain how we grab it. And it's 240 gigabytes, 700 million accounts, and 20 billion edges. And we compress that to fit on a laptop just like this one here. And that takes some doing, so I'll explain that as well. And then at the end, I'll show you that we're not just doing it for fun. It does work. It does achieve something. So I've been doing this now for 2 years. I started off at this really great startup called StarCount, which is a social media analytics startup done by Clive Humby and Edwina Dunn, who founded dunnhumby, which is the Tesco club card company. I've now left. That's why it says asos.com on my badge. But I'm still doing it because I do it at Imperial. I'm funded by the Royal Commission for the Exhibition of 1851. So I have an industrial fellowship. If any of you are thinking of combining education and commercial work, then I really strongly recommend applying to the Royal Commission. They're great. They fund 8 people like me every year. They give you £100,000 to spend 3 years doing research, and it's not that well known about. Or maybe it's a bit better known about now. Oh yeah, and this whole thing is in Python, obviously. So this is the problem that we started thinking about a couple of years ago. Loads of people were doing really cool stuff with social media. Most of them were looking at tweets and doing sentiment analysis. And so you'd be able to tell your company, okay, what do they think of your new product? Are people mostly positive or negative? But not a lot of people were really looking at the structure of the network. And so we had this problem in mind. If you're, say, a British company and you want to start selling your products in Brazil, what do you need to do to do that? And any management consultant will tell you, you need to understand your customers, you need to understand your competitors, you need to understand your distribution channels and your marketing channels. And the only real way to do that, I mean, you can start Googling it, but really what people do is they hire a management consultancy. And no disrespect for management consultancies, they're great, but they take 6 months and they charge you £1 million. And it's a bit annoying if they come back and say, actually, no, Brazil's not going to work for you, sorry. So what we thought you might be able to do, given that there are 300 million active Twitter users across the globe, is that you could perhaps take your brand, given that it's on Twitter, and maybe some of your products, maybe some of your star employees or people that endorse your brand, and put them into this magic Twitter machine. And this out would come what people who like your stuff also like in Brazil. And so that was the idea. So could we tell what your Brazilian fans' media titles of choice are, or their influencers, which footballers do they follow, and then we would know how you can launch your product in this new market. So that was the big idea. And we want to do this in real time because, well, for the same reason that we all love working in Python. So Python, for me, it connects my brain to the machine and back again. I try something out, it doesn't work. I'm like, try something again, and then it doesn't work again. But instantly, I get that feedback, and I can work really, really fast. I used to be a C++ programmer, and it's just not enjoyable anymore. Once you start doing Python, it's no fun to go back to C because you have to wait. And so I wanted to build a product that was like that was instantaneous. You put what you want in, it doesn't quite work, you try something else, you get the feedback. And the reason we wanted to do it on a single laptop is because we've been working with Hadoop and Spark, and I'm sure loads of people here have. It's completely the way the industry is going. And most people will stand up and tell you how amazing those tools are and how seamlessly they get them to work. That's a lie, or at least it's a lie in my experience. They're really, really hard. This is my stack trace from last week. There's an error in there. I ran this 10 times. I get 10 different errors. I don't understand what's going on. I have an engineer who has to fix all of these problems for me. It's just not easy to get cluster computing working. There's a huge amount of complexity. So if you can do something on a single machine, then that's at least how you should start. So this is what the whole thing, at a very high level, we thought might look like. You get your Twitter handles of things you know. You put them into this Twitter machine that gets out all of the similar stuff. So you might put 10 things in. You might get 4,000 things out of that second box. And then you take those 4,000 things and you structure them in some way. So you can look at, these are all the media titles, these are all the influencers, these are all your competitors. And then you make a pretty-ish picture like that. And then if you don't like what you see, maybe you hover over that bit and put that back in the front, and you get a new picture. So it allows you to explore this huge world of 300 million accounts interactively. So the first thing is to define what we mean by similar. And for us, the obvious similarity measure on Twitter is shared followers. So if there's a blog out there that loads of people that follow my company also follow, then it makes sense that that blog is important to me and that maybe I should be talking to that blog. So you can measure the number of shared followers, but the problem with doing that is that accounts like Justin Bieber have like 100 million followers, so they'll come up as being really important to everything. So you need to normalize it in some way, and the natural way to normalize these things is using something called the Jacquard similarity measure. And the Jacquard similarity measure basically takes that number of shared followers and divides it by the total number of followers of the two things. So it's the intersection divided by the union. And before I had this job, I used to work for an investment bank. And after that, I used to work in defense. So I used to have financial data or sensor data. And then I started working with social data. And it's horrific. It's like so much worse than any structured data set you can imagine, because there are these entities that exist in the social world, because it's real humans, or not real humans sometimes, that you just do not expect to see. So Twitter is full of robotic accounts created that run completely autonomously to do loads of crazy stuff. There are also an enormous number of people running what's called the follow-back strategy. So if you have a Twitter account, you've probably been followed by someone that has 10,000 followers and follows 10,000 people. And 30% of people that get followed by that person will follow them back. So what guys are doing is they're following 1,000 people a week. 300 of them are following them back. They're binning off all the ones that don't, and they're doing it again. So you can get like huge amounts of Twitter followers that way, but it doesn't say anything about what you're interested in or what you like. So you need to try and ignore those people. There's a massive, massive market for paid followers. So I might get in trouble for saying this if anyone from Twitter's here, but so Justin Bieber has 70 million followers. He doesn't. He has 20 million followers, and he's bought 50 million followers. Same with Katy Perry, same with Lady Gaga. There are also a ton of fake accounts. So the way a lot of cheap follower sellers work is they have this enormous conveyor belt. They set up a fake account. They follow loads of people, spin it to the back. Another one comes out and follows loads of people. This is my current favorite bot on Twitter. It's the International Space Station bot. So what happens is you follow this bot. I don't know how it knows where you are, but it somehow does. And when it's overhead, it sends you a direct message on Twitter saying, look, I'm there. And if you're outside and it's dark, maybe, you can see the International Space Station, which is cool. And this is an example of some of the junk that's all over Twitter. So these 4 accounts, they look pretty legitimate. They've got like Money Thread, Steph. They've got kind of normal names. But then you look at the description, and they're all the same description. It's all TwitZip, building a Twitter zip code infrastructure for consistent public use. I don't know why someone's made these. Maybe someone's experimenting. But stuff like this really messes up your data, so you need to be aware of it. This graph here, I've taken all 700 million Twitter accounts, and I've plotted the number that follow each number of people. So on the left there, that's the people that follow no one. On the right, someone follows 2 million people. And we expected this to be a straight line. This is actually a log-log plot. So there's loads of theories. In social networks, you get loads of log-log plots because power laws look like a log-log in a social when you plot them like this. And there's this really weird, well, you can probably see it from there, but this rabbit thing that's just sitting on top of the graph, so which we didn't expect to see. And the reason there's that thing is because that is at 2,000, and you can only follow 2,000 people on Twitter before Twitter blocks you. So there are these kind of factories that are selling fake followers. They just spin up an account, the account sells 2,000 follows, and then Twitter blocks it, so it goes to another one. And that's what all of that is. That's all manufactured accounts. OK, so that's the basic setup and some problems with Twitter. How do you then go about getting all of Twitter? Well, you need 3 things. So you need access tokens. Whenever you click log in with Twitter on an app, that's what you're doing. You're giving that app one access token. Then you also need some engineers to build the thing. And as we found out, you need a pretty damn good internet connection. So when we set about doing this, we had 3 apps, and we actually had 1,000 access tokens, which is more than most people have. But you can easily get 10 if you have some mates and a few email accounts. So you can have a go at this. And we looked for libraries, and we found a really cool library called Tweepy, which is a Python library for downloading Twitter stuff. And we ran it on a single machine, and we thought, let's try and get all of Twitter. And it was going to take us something like a year. So, OK, well, that's not really going to work. What's going on there? And the problem is that when you run an app like that, it makes a request to Twitter and then just sits there and does absolutely nothing while Twitter at some point responds, maybe 2 seconds later. So almost all of your processing time is just waiting for Twitter to get back to you. So we thought, OK, what we'll do, great plan, is we'll have like loads of those. So we had 200 of these on separate threads running at the same time. We thought that'll run 200 times faster. But it doesn't. So if you know anything, well, a lot about Python maybe, you know that there's a global interpreter lock in Python. So when you run multi-threaded code, it's not actually running in parallel, because it all has to respond back to this global interpreter lock. That's how you get the interactivity. But it means that you don't get that parallelization. So it didn't really work. But at this point, we discovered that there are actually 3 distinct paradigms for doing this kind of thing. There's the one on the left there, which is what I tried to start with, which is just having one thread. Then you can have multiple threads. But the magic really happens on the right with asynchronous programming. So, Python has this really cool library called Twisted, which gives you an asynchronous programming reactor loop. And what asynchronous programming does is it doesn't wait anymore. So when you send off your request, you don't wait 2 seconds. You just end up firing off like thousands and thousands of requests. And when something comes back, the reactor knows just to grab it, process it, and keep firing and firing and firing. So when we switched from 200 threads to 1 asynchronous thread, we actually crashed the internet of our building. So we were in the BBC annex. It was really, really annoying for everyone working with us. I've got some tips for asynchronous programming in Python, because I spent 3 months doing this, and it was a horrible 3 months of my life. So the first thing is read a book, and actually read that book by Dave Petikolas. It's free. It's at chrondo.com. It takes about 10 hours to read. So the number of times I'd read one part of it and then be like, oh, I can't be bothered to read it. I just go and try and hack along. And that's what I recommend doing normally when you program, right? You program, you hack along, something doesn't work, you go on Stack Overflow, you find the answer, you keep going. That's like the way to learn programming. It's not with asynchronous programming. Read a book. And my second big tip for asynchronous programming is draw it out, because you have everything goes the wrong way up. So you have a reactor that fires things the wrong way up the stack. So you can't debug in a normal way. And things don't go through the code in a linear fashion. They can move. So you need a picture, or it's really, really hard to debug and know what's going on. So this is the architecture we ended up with. Each one of those clients is a twisted, asynchronous thingy. They all scream at Twitter. And this guy at the top, the server, is telling them which request to ask for. And it also has a queue of access tokens. So every time an access token gets burnt out, the client says, I've used up this one. It goes to the back of a big queue. We put a lock on it for 15 minutes, and then it can flow back through again. This managed to get all of Twitter in 2 days. OK, so that's how you get the data. 240 gigabytes, full Twitter network, 700 million accounts, 20 billion edges. That doesn't fit in memory on a laptop, at least not a laptop that's going to be built for the next 1,000 years. 1,000 maybe a bit of a big shot there, but not at the moment. So you need to compress it. Now, what you normally do when you want to compress data, the first thing to try is just sample it. But you can't sample network data, because these points represent humans or bots or things that are unique. There's no IID-ness at all there. And you can't there's no way to know which vertices to choose or which edges to cut off. And you can't follow edges, because then you just find like the UK and you're trying to learn about everything. So you can't sample, basically. But there is this magical thing called min hashing, which was invented by Andre Broder in 2000. He's now a Google senior fellow, so he's pretty awesome. And he came up with this idea where you can convert enormous sets. So each one of those things might be Justin Bieber with his 100 million followers. And you can convert him into a fixed length array of integers. And by just comparing, if this is Justin Bieber and this is Katy Perry, you just compare element-wise. So these ones are the same, not the same, same, not the same. So if 3 were the same, there were 5 in total. So the Jacquard estimate is 3/5. So it's super easy. And that kind of thing takes nanoseconds on a computer. Instead of trying to compare two things that are 100 million elements, this takes a second or two, or longer. This is probably the most boring part of my talk coming up next. It's 5 slides. I'm trying to explain how min hashing works. Please bear with me. So this picture here is a Twitter world where there are only 8 Twitter accounts, and I'm trying to compare a company and a blog. And here, the company and blog are both followed by the first Twitter account. None of them are followed by the second. They're both followed by the third. Only the company is followed by the fourth. They're both followed by the fifth, none by the sixth, both by the seventh, and only the blog is followed by the eighth. And to take the min hash of this guy, you just take the minimum value where each one has a follower. So 1 and 1. And then what you do is you randomly commute all of the accounts. Oh, wrong way. And take the minimum again. So now the company's minimum is at 1, and the blog's minimum is at 3. And you just keep doing that. So I randomly commuted it again. Company's minimum's at 3, blog's minimum's at 4. And again, and again. And that seems to me completely random, but it's not. So the probability of the blog and the company having the same min hash value is exactly the chance that you hit one of these guys, where they both agree, before you hit one of those guys or one of those guys. Okay? And the number of these guys is the intersection, and that plus that plus that is the union. So the probability of any one of those min hashes being the same, getting a collision, is that number. And that is just that. So I've got no idea how Andrew Broder came up with this, or what he was thinking about, but it's awesome, and it's used all over the internet. There's a bit of a trade-off between the length of the min hashes and the accuracy and the performance. So the longer the hashes you have, the more memory you need, the longer it takes, but the more accuracy you get. And so we tried this with 400,000 different combinations of people. And actually, we worked out it's based strictly a binomial distribution anyway, so we didn't need to do this. But around 1,000 min hashes, the whole data set would fit in 4 gigabytes, so roughly RAM of a pretty rubbish laptop. And the error is only 0.001 in Jacquard space, which it turns out for our problem is absolutely fine. So once you've got the min hashes, it's really, really quick to compare and get Jacquard estimates. But getting them is a super pain because you have 20 billion edges and you're tackling 1,000 hashes for every single edge. So you've got like 20 trillion calculations. And when we originally did that, it took 6 days in pandas just trying the first thing we could think about. So what we ended up doing is coding it all in Cython. So Cython is the Python C bridge project. Python is completely rubbish at loops. So you should never really be doing big loops in Python. But Cython is basically C, and it's awesome at loops. And there are a few tricks you can do in Cython. So you can have strongly typed variables. And the reason Python's awful at loops is because it checks the bounds on the arrays every single time. And you can turn that off in Cython. And you can also stick your arrays in contiguous memory. So if you want to do something really quickly, Cython is absolutely the way to do it. And I strongly, strongly recommend, in anything you're doing when stuff takes too long, profile your code. So the profiler I use is built into PyCharm. PyCharm is my favorite IDE. But there's loads and loads of free Python profilers, and Prune and LPrune are built into IPython. They're also great, so totally profile your code. And this book is the source. I think these guys are both speaking here. This book is incredible. If you want to do fast things in Python, get it, read it. So now we've got the data. It's compressed. It fits in memory of a single laptop. But we still need to query it in real time. So real time means less than 1/4 of a second for me. And you've got a bit of a problem because there are roughly 1 million of these things I've min-hashed. So I min-hashed the 1 million most interesting accounts on Twitter, the largest million. And so if you want to put 10 accounts in and compare every single one of them to every single one of those things, you're looking at 10 million different comparisons, which is hard to do in 1/4 of a second. And the solution to that problem is something called locality-sensitive hashing. So the way locality-sensitive hashing works with min hashing is you kind of band up the min hashes and hash each one of those bands and then into a little box in here. And things that agree on a whole band go into the same box. And yeah, that wasn't a very good description. It's quite an involved subject. I can talk about it afterwards if anyone's really interested. But the key point about locality-sensitive hashing is it's constant time, roughly similar lookup. So it gets you from something not real time to something real time with a little bit of error. And so we have this system in the end where you put in a product and brand handles, you fire it into locality-sensitive hashing, outcome maybe 4,000 things that are pretty closely related to your product and your brands and your people. And then we put those 4,000 things through another great library called iGraph, which is available in C. I think it's written in C, but we use the Python version. There's a cool Python wrapper of it. And that gets you pictures like this kind of thing. So it does community detection. We use an algorithm called walk trap. Cool. And that's a real-time querying now on the full Twitter graph. So again, 700 million accounts, 20 billion edges, real-time querying on a laptop. And that's all great, but nowhere in anything I've said have I given any real indication that this works at all. And it's quite hard to prove that that kind of process works, because I'm saying, all right, I put in a company and some other people, and then I get out things that are related. It's difficult to imagine a scientific evaluation of that process. So what we actually did is we went on Wikipedia and we tried to match every Twitter handle we could to a Wikipedia page. And Wikipedia pages have a load of tags attached to them. And so we extracted these tags and attached them to Twitter handles. And we did this for loads of things. So we did this for things tagged with travel, we did it for models, we did it for MMA fighters, various sportsmen, athletes. We even did it for porn stars. And then we put 30 people from each of these groups into our machine, and we looked at how many from the group came out again of the other side. So the ideal situation is that you put 30 in and you get the whole rest of the group out. And some people have done things similar in the past, and they've identified the state-of-the-art algorithm for doing that, and it's an algorithm called personalized PageRank. So at these charts, personalized PageRank is the red line. There's two variants of what we did, and they're the yellow and blue lines. And this measures the total recall. So a recall of 1 would be an ultimate win, almost impossible. But the takeaway here is that we're higher than the red line. To give a bit more flavor to it, I zoomed in on, that sounded like that went weird. Can everyone hear me still? Okay. I zoomed in on one of the communities that I thought people would be able to understand. It's the alcohol community. So we put 30 things that were labeled as being alcohol brands in, and this is what comes out. So we clustered it using this walk trap algorithm, and it's not really a big surprise, but it's still cool that it works. The alcohol is clustered into 4 different categories. So in the bottom left there's beer, the bottom right is cider, the top left is spirits, and the top right is wine. And we've zoomed in on the cider and just pulled out some Twitter logos, hopefully just to convince people that this thing really works and I'm not just drawing pretty pictures. I wanted to do this with porn stars, but some of their pictures were not appropriate. So I also looked at the US Republican Party. So I put into the machine this time all of the now former candidates for leader of the US Republican Party. And I wanted to see if there were factions within the US Republican Party. So does it split into major bits, or are there 2 factions? I wasn't really sure. And so here, this is the mainstay. These are all the major Republicans. This here is some media titles and some lesser Republicans, governors and things instead of senators. Up here is Ben Carson. Ben Carson. I don't know if you know, he's like a doctor who tried to become president, but he's not really a mainstream Republican. And up here is Donald Trump. So Donald Trump is barely connected to the Republican Party. And his only connection is this one. And that is Megyn Kelly, who actually really hates him. So he's only connected to the Republican Party by someone who despises him. OK, so what we've done then is we've downloaded the full Twitter graph, which is huge, 240 gigabytes. We've compressed it to fit on a laptop, so 4 gigabytes, or a little bit more, but an 8 gigabyte laptop would be fine. We've shown that you can query that data structure in real time, so you can, within a quarter of a second, you get results back. You can iterate them, get them in again, iterate them. People at StarCount use this. And then we've shown how you can cluster those using WalkTrap and get interpretable pictures out, which can tell you something about the real world. I owe a debt to a couple of guys at StarCount for this presentation. Donal Simi, who's a really cool data scientist there, did all of the Siphon stuff, so he got the min hashing down from 6 days to an hour, which I didn't think would be possible. And Josh Levy-Kramer, who actually spoke here last year, did some of the slides. I don't know if I'm allowed this next slide. I'm going to try anyway. So I work at ASOS now. We're hiring. Speak to me afterwards if you're interested. Am I allowed to do that? OK, good. Right, then. And that's the end of my talk. Thank you so much for listening.
Thanks. So I just wanted to clarify, after you found the neighborhood using locality-sensitive hashing, what were the connections between the members of the neighborhood? Were they follower connections, or were they associations like Jacquard similarity?
Yeah, so that's a really, really good question. I completely missed out that bit of the talk because it would have been too long. But what we actually do is we take these 4,000 people, and then we use the min hash signatures again to reconstruct a weighted subnetwork, and then we do community detection on the weighted subgraph, which is why we use WalkTrap, because it's really good for weighted networks.
So do you apply any kind of sparsification rule to prune edges from that? Or?
Well, so we don't need to, because it's only 4,000 vertices. Yes, you're right. It is fully connected, but WalkTrap works with fully connected graphs.
Sorry, thanks very much for your talk. I just wondered, like, in terms of Twitter and the rate API, maybe I missed something there, but how did you handle that kind of aspect of it? Because I believe that they're rate limiting you according to developer APIs.
Yeah, so they super rate limit it. We had 3 commercial apps. We collected 1,000 access tokens. We put them in this big queue and just spun through them all.
Okay, right. And then eventually, I guess the tokens expired, and that's when you put it at the end and then wait 5 hours or however long.
15 minutes.
15 minutes, okay.
Yeah, so the way it works is I don't know, we'll go back to that picture. Oh, it seems to be stuck on that one. Oh, here we go. Oh, no, there we go. So this guy here manages a queue of 1,000 access tokens.
Okay, yeah.
And it gives them to these guys when they scream out when they're done, and they say, okay, we've burnt out that one, and this sends a flag back here which says put a lock on that for 15 minutes.
Yeah.
And you just spin through the queue.
Yeah. We tried doing something very similar with Facebook, so thank you.
Yeah, Facebook's hard as well. Yeah. Facebook's like less access.
We're going on to talk about that in my talk next.
So.
When you do the whole process, the locally sensitive hashing, how much time does it take you to do the indexing, and how much time does it take to compute the like the similarities?
So the whole thing runs in under a quarter of a second.
Sorry?
The whole thing runs in under a quarter of a second. So you choose your seeds, you put them in, you hit return, and like in real time, it returns those pictures, those kind of graphs. To index the LSH table takes half an hour.
Okay. Okay, thank you.
On this slide, do you have any tips for, you mentioned it was pretty tricky debugging asynchronous twisted apps. Do you have any tips for debugging the app and deploying to multiple servers?
Yeah, so the main tip I had was, so we had this picture. We had loads of these pictures for every little bit of it, because you never know when the entry point is into the code. because when you get a response back, it just triggers off a new chain of execution, which is really, really confusing when you're trying to debug. So we had this picture of this kind of loop of how all of how the code was flowing, and that really helped us out. So we have other pictures as well which show, so in asynchronous programming, you have callbacks and you have error backs, and if you like satisfy an error back, you can go into the callback chain again. So having those drawn out with like little boxes showing which error back leads to which callback, I think is absolutely key.
Okay, thank you, Ben. If there's no more questions, thank you for the great talk.
Thanks.